Welcome back to PRATIK Academy. In last video we have seen classifications of vibrations and also vector representation of vibrating system. In this video we will see analysis of vibrating systems. So let's start. There are three methods of analysis of vibrating system, that are equilibrium method, or it is also called as Newton's method or D'Alembert's method. Second one is a energy method. Third one is a Rayleigh's method. Okay, so there are three methods. Let's see it one by one. So first is Newton's method. It is simply Newton's second law. It is at equilibrium state, accelerating force is equal to restoring force for linear systems. In case of angular systems, accelerating torque is equal to restoring torque. Accelerating force means force which is responsible for acceleration or which produces acceleration in system, and restoring force means the force which brings back system to its equilibrium state. Okay, so apply this for first longitudinal system. So longitudinal system classical example is spring mass. So consider a spring having initial length del, and when we attach mass m to one of the ends of spring, then it deflects by some initial amount delta st. This is static deflection of spring. Okay, at this condition, if we apply Newton's law, then here downward force weight is balanced by spring force. Here K is spring stiffness, that is nothing but resisting force for deformation. It is per unit deformation, that is Newton per meter. Here deformation of spring is delta st, so spring force would be K times delta st, but both are in opposite direction, so mg is equal to minus K delta st. This will be our first equation. Okay, now consider this mass is displaced from its equilibrium position by some amount x and released. Then when we move this system in downward direction, due to that motion it gets acceleration and hence accelerating force in downward direction. That accelerating force is equal to, or total accelerating force is this weight which is acting in downward direction plus due to movement we get accelerating force mx double dot. Okay, at any instant, say x, the total deformation of spring is x plus initial deformation is delta st, so total resisting force in upward direction will be K into x plus delta st. Okay, minus sign indicates both are in opposite direction. Then solving this bracket, we get mg plus mx double dot is equal to minus kx minus k delta st. Then from equation 1 we know that here, from equation 1 we know that mg is equal to minus k delta st, so cancelling these two we get mx double dot is equal to minus kx, that is x double dot plus k by mx is equal to 0. Then if we compare this equation with standard SHM equation for linear motion or longitudinal motion, our standard equation is x double dot plus omega n square x is equal to 0. Omega n square is our natural frequency, so comparing corresponding terms we get natural frequency of system is under root k by m. Equation 1 is equation for longitudinal system. So this is for longitudinal system. Now next is considered for transverse system. So classical example of transverse system is our Pendulum. Okay, pendulum consists of mass which is attached to string having length L. Here we assume that length of string is unstretchable and its mass is negligible. So total mass of steam is concentrated at this ball or bob. Now consider if we deflect this system in by some amount theta in this direction, then due to this deformation or movement it gets accelerating torque here in this direction, and at any instant due to its weight it will try to move in its own direction or will try to move its in equilibrium condition, and this is due to some restoring torque. Then find its values. First, accelerating torque is equal to, here we take I theta double dot, because we know that in case of linear we have mass, in case of linear we have linear displacement, similarly in case of linear motion we have force. Corresponding terms in angular motion are, for mass there is a mass moment of inertia, for linear displacement we have angular displacement, for force there is a torque. These are the corresponding terms for linear and angular motions. So accelerating torque will be equal to mass moment of inertia into acceleration, that is theta double dot. Okay, this is our second equation. Then restoring torque. Okay, for restoring torque we require force and perpendicular distance. So our accelerating torque is in this direction, so restoring torque required or restoring force should be in this direction opposite to this accelerating force or torque. So resolving mass or weight into two components, one component is along string and one component is perpendicular to string, and this component is in direction of or towards direction of our equilibrium position. So this force and perpendicular distance is L here. So torque is mg sin theta, this is the force into distance L. So resisting torque will be minus mg L sin theta. Now equating both terms we get I theta double dot is equal to minus mg L sin theta. Then for very small angular displacement we can put sin theta is nearly equal to theta. This is for very small angular displacement. Then I theta double dot plus mgl theta will be 0, equal to 0. Then as we have seen, or we are assuming that mass of this length is negligible, total mass is concentrated at center point of this ball, then I will be equal to m into radius of gyration. Here radius of gyration will be L, so I is equal to ml square. So putting this value we will get equation L theta double dot plus g theta is equal to 0. Now this is our equation for transverse vibrations comparing with standard equation, it is theta double dot plus omega n square theta equal to 0. This is standard equation of SHM in angular motion. Comparing corresponding terms we get here, comparing corresponding terms we get omega n is equal to under root g by L. So this is for transverse system. Then next system is torsional vibration. In case of torsional vibration, we know that there is one rotor which is attached to shaft, and when we move this rotor in clockwise or anti-clockwise direction, it will start vibrating along this direction to and fro motion. And consider here KT, that is torsional resistance. This is torque per unit angular displacement. Okay, torque per unit angular displacement similar to our linear stiffness or spring stiffness. And I is a mass moment of inertia. Then when we displace this rotor in by some amount theta, then accelerating torque will be here I theta double dot. similar to transverse vibrations. Then restoring torque, here you know that torsional stiffness, it is torque per resisting torque per net displacement is kt, and if displacement is theta, then total resisting torque will be kt into theta, that is equal to minus kt into theta. Then equating both two, we get I theta double dot is equal to minus kt theta, so I theta double dot plus kt theta equal to 0. So theta double dot plus kt upon I is equal to 0. Therefore omega n is equal to under root kt upon I. Here I, this is mass moment of inertia of this rotor, not of this shaft. Then additional information is we have torsional equation for this shaft, that is c theta upon L is equal to 2 by j. Here consider this torsional stiffness is of shaft and I, this is of shaft material, this is for rotor, is considered here. So this is nothing but torque per unit deformation deflection. So by torsional equation we have c theta upon L is equal to 2 upon j, so 2 upon theta is equal to cj upon L. From this we can calculate torsional stiffness. Okay, so this is Newton's method for linear, transverse and for torsional system. Next system is next method is energy method. Okay, this method said that total energy of system is constant at any instant. Total energy of system is constant at any instant, and total energy is consist of kinetic energy plus strain energy or potential energy at that instant. So kinetic energy is acquired by mass, and strain energy is due to elasticity, or potential energy is due to elasticity, and it is stored in spring. So first consider longitudinal motion here, or linear vibrations, longitudinal vibrations, there is a spring having length del and having stiffness k. When we attach mass, deflects by some amount. Now when we attach this mass, when we pull this mass by some amount, say x, then at that instant by energy method total energy is constant. So calculate energy at this intermediate position. We are considering intermediate position, not extreme positions here. So total energy is equal to kinetic energy plus strain energy at that instant. Kinetic energy is equal to then 1/2 m velocity is x dot square. So kinetic energy will be x dot square here. Then strain energy, formula for strain energy is average resisting force into deformation. When system is at equilibrium, deforming forces are 0. When system is at distance x, deforming force will be k into x. So average force is 1/2 of average of 0 plus kx, that is kx by 2 into deformation here x. So strain energy will be 1/2 kx square. Then total energy, putting in total energy equation, we get this. Now differentiating with respect to time, we get d derivative of total energy with respect to time is equal to derivative of this kinetic energy with respect to time, derivative of this strain energy with respect to time, taking constant terms outside here, and here derivative of constant is 0. Here 1 by 2 k is constant. Then derivative of x square will be 2x, here 2x into x dot. Okay, and derivative of this velocity square is 2x dot x double dot. Then cancelling common terms, you get mx double dot plus kx is equal to 0. This is nothing but equation for longitudinal system, and comparing with standard equation we get natural frequency is under root k by m. This is the energy method for linear system. Now consider energy system for transverse vibrations. Then again consider classical example is spring pendulum having length L attached to mass m at the end of spring. Then let consider at any angular deformation theta we have total energy is constant. Okay, it is derivative of total energy is equal to 0 with respect to time. Then kinetic energy is equal to 1 half. In case of linear we have seen m x dot square, so in angular we get 1 half I theta dot square. Similar terms for linear and angular motions. So this is one. Now potential energy. Okay, here when mass deforms by or displaced by some angular deformation, acquired some angular displacement, then vertical height is changed by amount x. So change in potential energy here is mgx. So we get here mg here for x is nothing but this total length is L, because this is the length of our string. Then this height will be this is L at an instant, theta angle is theta, so this height will be our L cos theta. So total height minus this height will be L minus L cos theta. So our potential energy at that instant is mgl 1 minus cos theta. Okay, then total energy will be, equation will be total energy is equal to this kinetic energy plus this potential energy. Then differentiating with respect to t and making constant terms outside of derivative, we get here 1 half ml square derivative of theta dot square with respect to time plus mgl derivative of 1 minus cos theta with respect to time. Taking derivative or equation, and here derivative of total energy which is constant equal to 0. Then equating to 0 we get equation L theta double dot plus g L theta is equal to 0. This theta double dot plus g by L theta is equal to 0. Therefore natural frequency will be, comparing with standard equation, this theta double dot plus omega n square theta is equal to 0. Natural frequency will be under root g by L. So this is for transverse vibrations. Okay, now next is torsional system. Again for torsional system, at any instant t to total energy is constant. So energy is constant here. Total energy is sum of kinetic energy plus strain energy. Then kinetic energy at any instant is 1 half I theta dot square. Then strain energy will be torque into deformation or angular deformation. So here average torque into angular deformation, similar to our linear deformation. When deformation is 0, there will be no any restoring torque. When deformation is theta, restoring torque will be kt into theta. Kt is the torque per unit deformation into deformation theta, so kt theta and divided by 2. Then angular deformation is theta, so strain energy will be 1 half kt theta square. Then putting in this equation and differentiating with respect to dt as previous, we get equation I theta double dot plus kt into theta dot, I theta double dot to kt into theta is equal to 0. Then theta double dot plus kt upon I theta is equal to 0. So our equation becomes, comparing with standard equation, that is theta double dot omega n square theta equal to 0, we get omega n as a under root kT upon I. So this is energy method for longitudinal vibration, transverse vibration and torsional vibrations. The next is Rayleigh's method. This Rayleigh's method is used to find out natural frequencies. This by Rayleigh's method we will not get any equation for system. It only gives our only gives natural frequency. Okay, so it is used to determine natural frequency of system. Then just 1 minute here. Natural frequency of system. So before going to see this, let's recall this video, or I will suggest to see second video again. In that there is one point remaining. While explaining this, the maximum value of velocity will be when our this omega t is equal to 0. This cos theta will be 0, or velocity will be maximum, and that maximum value is x omega. Okay, x into omega. And acceleration maximum will be when theta is equal to 0, theta is equal to 90 degree, we get acceleration is maximum, that is minus x omega square. So maximum velocity is x omega, that is amplitude into angular velocity, and acceleration maximum is minus x omega square, or magnitude is amplitude into angular velocity square. So just check this. Okay, now here equation is, or Rayleigh's method is comparing kinetic energy at equilibrium is equal to potential energy at extreme position. Okay, we will consider only spring mass system because there is a time limitation of this video. Okay, spring mass system, consider here, initially consider it is at equilibrium position. When we take this system at amplitude or extreme position, then this capital X is amplitude. Then at mean kinetic energy is, there is only kinetic energy because there is no any deformation. Total energy will be kinetic energy. Then maximum kinetic energy will be 1/2 m x dot x max square, it is maximum velocity square. Okay, then maximum velocity is equal to omega n into x, because system is vibrating with its own frequency. Frequency will be natural frequency. So x max is, or velocity max is omega n into x. So putting this value we get 1/2 m omega n square into x square here. Then again at extreme, again potential energy maximum will be average spring force here at initial, at equilibrium 0, at extreme spring force is k by x divided by 2. Okay, then potential energy is maximum, that is 1/2 k into x. Sorry, kx square here, this is, so there is a mistake. Potential energy is average spring force into deformation is x, so it is 1/2 k x square here. So 1/2 k x square get cancelled here. So our equation is omega n square, here 1/2 get cancelled, it is k by m. So natural frequency here is under root k by m. Sorry for these corrections. Okay, so in this method, sorry, in this video we have seen analysis methods for 3 systems. One first is our energy method, then Newton's method, and this Rayleigh's method. I am extremely sorry for these corrections. Again, if you have any other doubts, we have provided our contacts here. You can contact us. We are always happy to hear your suggestions for improvements. Thank you for watching.